The other task that you have as a group is to remind me to hit record. I have no idea what this is going to look like. I'm glad we're starting because this looks funky. We'll test this out. Interesting. Okay. Okay, so let's take a look at what we've got here. This is our comparison between intermolecular forces and intramolecular forces. So intra. So the intramolecular forces are things that take place within one molecule. Okay, so these include covalent bonds, ionic bonds, things like that. The intermolecular forces are the forces between molecules. So if you have two molecules that are close together, how are they going to interact? Right? So that's what we want to focus on because those are going to show up in chapter 13. So there's four types of intermolecular forces that we talk about. The first one being London dispersion forces. Yeah, I need to practice. So these blue circles here, we're going to try to represent dispersion forces of these. So every atom is going to have a type of dispersion force. And that is because they have electrons. Right? The more electrons, the more we can have dispersion forces. So basically what happens with a dispersion force is we can kind of imagine we're representing an atom by this set of circles. The center represents the nucleus, and the blue represents some electron clouds. Okay, very easy drawing, certainly not accurate, but we're going to try to imagine it like this. At some point in time, those electrons can all sort of move to one side of the atom, just sort of randomly. Okay? And what that then does is it creates a partial negative charge. Minus VE is negative. I might write that a lot this semester. So where the electrons are, they have a negative charge, right? So they create a density in that area of negative charge. The opposite side of that atom then will have a partial positive charge, plus VE, positive. And what that does is it induces a dipole, basically creates this sort of instantaneous dipole, and it affects the other atoms around it. So now the atom next to it, the minus part lines up with the plus part, okay? Electrostatic attraction. And this happens across a whole sea of atoms. Okay? They can switch. Now we have the negative on the right-hand side, for instance, and then it induces the dipole the other way. Another term that you may have heard about that's related to this, which describes this, is polarizability. So if an atom is polarizable, it means it can have a pole, right? Positive side, negative side. Some people, and I think the textbook now uses the word sloshiness of electrons. So if your electrons are freely able to move, okay, they can slosh to one side of an atom or slosh to the other side. The more sloshiness, the more polarizable, the greater those forces are. So even noble gases, which we know do not react, right? We can take a gas and condense it down into a liquid. We can make liquid helium, for instance. But in order to be able to do that, we have to make those atoms interact. And the way they're interacting is with this dispersion force. So every atom is going to have some kind of dispersion force. When we say what kind of intermolecular forces are present in whatever, number one is always dispersion. Okay, it's always there. Questions on that? Okay. What kind of forces are being represented in this picture here with the green and blue spheres? Dipole, dipole. So here we have atoms that are bonded together. We can say this is HCl, as it works, where the chlorine has a negative net negative charge and the hydrogen have a partial positive charge. And because of the arrangement of, or because of the electronegativity of the chlorine, we create a dipole within the molecule. So now we have to have two atoms interacting, okay, in order to have a dipole-dipole type of force. And so what we're showing here with the pluses and minuses, these are partial positive and partial negative. Negative is the green, positive is the blue. And look at what the arrows between the molecules are doing. They're showing interactions. And you'll notice that the positive charge on, we'll say it's the hydrogen, is interacting in some way with the negative charge on what might be the chlorine. Okay? This is the dipole-dipole interaction. The dipole-dipole is not between the two atoms that are in the molecule themselves. If this is HCl, then this is a covalent bond between the two atoms here. But the arrows are showing the intermolecular force. Intermolecular forces are not going to be as strong as the intramolecular forces. That diagram at the very beginning. Okay. So one kind of interesting thing that dipole-dipole forces do is they kind of create a network. And so you can see as we've got positive attracted to negative and attracted to positive, and then we've got a negative attracted to a positive and things like that. So you can kind of imagine that the molecules have to arrange themselves in a way that allows for these interactions to take place. Okay. Dipole-dipole forces then, because of the way they're interacting, are stronger than the dispersion forces. All right. So we can take a look then again at our sort of spectrum of forces from weak on the left to stronger on the right. We have our dispersion forces, then we have our dipole-dipole forces. Then we have two others. We have hydrogen bonding, and we have ion dipole. Okay. So this figure is representing hydrogen bonding. Hydrogen bonding only occurs in certain molecules. The hydrogen has to be bonded to a nitrogen, an oxygen, or a fluorine. Okay? So here we're going to assume this is a water molecule. So we have H2O, 2 hydrogens bonded to an oxygen. The bonds between the oxygen and the hydrogen are not the hydrogen bonds. Those are covalent bonds. But the bonds that are shown by the dots, those are our hydrogen bonds. So we've got a hydrogen, this is weird. Hydrogen interacting with an oxygen, but it's not a covalent bond in that case. That's a hydrogen bond. Right, those are easy things to get confused. Which one is the hydrogen bond? Again, creates a really interesting network. And hydrogen bonds are traditionally stronger than our London dispersion, of course, and stronger than the dipole-dipole. Okay. So you're going to see hydrogen bonding coming up in water. You're going to see it with ammonia as well. Those are 2 classic examples. There are others, of course, but those are the ones you're going to see the most. And then in the one last minute, just so you've seen it, ion dipole, okay? So an ion dipole interaction, this will definitely come up in chapter 13. We're going to talk about dissolving ionic substances. So when you dissolve an ionic substance, you create ions. And then we can have, if we dissolve it in water, we can have water molecules arranged around that. And those water molecules are going to arrange in a particular way based on the charge of the ion that's surrounding. So you can see here we've got a negatively charged chlorine, and our partial positive charge on our hydrogens are pointing towards that. Okay? Opposite with the sodium ion. Okay, take a look at this. Right? If you have questions, feel free to step on down. We've got a couple of minutes.